Section 3 of Chapter 6 and Section 1 of Chapter 7 is what we're going to be talking about. Electric field strength. So we already talked about electricity being a field force. What does that mean? Yeah, we feel force without touching, without physical contact there. So something is going on, and it's very interesting if you try to think, so what is really going on if nothing is touching? What is providing that force, that pull, or that push? I don't know if you've ever thought about that. What is providing the actual push? Or you think of magnets, which is a field force. When you have two magnets, you can feel that force, but there doesn't appear to be anything in there. What is actually doing the pulling? You ever thought of that? What's actually doing the pushing? Don't know if you've ever thought of that. So we'll have to wait until we get into the quantum mechanics level of what is actually going on. But I want you to think about questions like that when you see things. What's going on here? I mean, something is being pulled together. What is happening that makes those things pull together? So that's what physics hopefully does for us, is answer some of those questions. And you may not be surprised that we don't know all the answers. But anyway, electric field, the region where electric force on a test charge can be detected. So the only way that I know there's an electric field is I have to have a charge in that electric field. Because just having an electric field won't make any force go on. When do I have an attractive force going on? Opposite charged particles, opposite charges. Or repulsion if I have the same charges. So I have to have another charge in an electric field, or there's not going to be another force. So we call that a test charge. SI units of the electric field, E, electric field strength, so capital E, we are going to use it, is newtons per coulomb. So how much force per unit of charge? That's what our coulomb is. What was the charge of one electron? How many coulombs? Do you remember what that was?
8.99 times 10 to the 9.
There's coulombs constant. Electric charge, the charge of an electron, the basic unit of charge.
19.9.
Something of 10 to the negative 19.
Negative 0.6.
There you go. What page is that on?
550.
550. There's the charge down there. The direction of the electric field vector, E, is in the direction of the electric force that can be exerted on a positive test charge. And this is going to carry through when we get into current, the direction of current. It's the direction that a positive charge would be moving. So if I have an electric field that is in that direction, that means it would be coming from some sort of positive. And what direction would a negative, I guess I could do E, though I didn't mean to. What direction would a negative charge be moving? Towards that positive charge, or I guess I should have drawn it a little better, towards the left, not towards the right. So the direction of the electric field is the direction that a positive charge will move. So I can remove this, and you would still know the answer to the question. What direction would a negative charge be moving in that electric field? To the left. Because the direction that the electric field is drawn is the direction that a positive charge would move. So a negative charge is going to do exactly the opposite thing. So you want to remember, like I say, that relationship. We always are referring to the direction a positive would go when we're talking about electric fields, or later on when we talk about currents. That is going to be true as well.
An electric field is a region of space around a charged object in which a stationary charged object experiences an electric force because of its charge. The electric field at a point is defined as the electric force that would be exerted on a small positive charge, called a test charge, located at that point. The The electric force, like any other force, is a vector quantity. The strength of the electric field at a point is defined as the magnitude of the force acting on the test charge divided by the charge of the test particle, which is always positive. The direction of the electric field at a point is defined as the direction of the electric force that would be exerted on the test charge.
And since the test charge is positive, it's the direction that a positive charge would move. So the electric field is going away from that positive Q, and it's going towards this negative Q. Electric field strength depends on the distance you are away. Should be fairly obvious. If I have in my left hand here my charge, and here's my test charge in my right hand, if I get farther away, what do you think the force is going to be on it? Weaker. Less. So electric field exists in a region around a charged object, and the strength due to that point charge, here's our first formula for today. So there's Coulomb's constant again. The test charge, that's what Q is, whatever you're using. So whatever charge that happens to be divided by the distance away squared. So let's try a problem. Oh, we'll calculate the net electric field first, I guess, and then we'll try a problem.
Consider two small charges, one positive and one negative. Using the superposition principle, you can calculate the net electric field at any point. Choose a point P directly above Q1. First, calculate the electric field produced by each charge at point P, and then find the vector sum of these fields.
So if I want to know the electric field strength right there, we're going to use, I moved it already, that lovely formula a minute ago. This is our Q divided by that distance.
Remember that the electric field at a point is the electric force that a small positive charge would experience at that location.
So that means this is going to be a vector pointing in what direction from this point? Towards the negative, because it would be pulled towards that one.
The magnitude of the electric force exerted on the test charge by Q1 is given by Coulomb's law. Q1 and Q0 are both positive, so they repel each other.
They're referring to this one. Then they switched after they drew this line. Or maybe they haven't talked about this one yet. I was talking about that one.
Since Q2 is negative, the force it exerts on Q0 is attractive. The strength of the electric field at point P produced by Q1 is the force divided by the charge Q0.
So Q1 is this positive one, and Q2 is this negative one.
The strength of the electric field produced by Q2 is found by an identical procedure. The forces on the test charge have been replaced by electric fields at a point in space. Now the x and y components of each electric field can be found separately. Then the components can be added to give the x and y components of the net electric field, which are shown here.
So the only one that is at an angle is this E2 electric field by this negative one. So we had resolved it so we could add together the vertical and the horizontal.
These components can be added by drawing them to scale on graph paper. E-tote, the magnitude of the net electric field, can be measured with a ruler. The angle phi, the direction of the net electric field, can be measured with a protractor.
We will not be doing it graphically measuring it. We will be doing it with trig to get the value.
Usually, however, the Pythagorean theorem and the arctangent function are used to find the magnitude and direction of the net electric field.
All right, so now we're ready to try a problem. 565, number 2. And these are the type of things that show up, later on homework or on tests. So we'll work through this one. 565. A proton and an electron in a hydrogen atom are separated by an average, on the average, by 5.3 times 10 to the negative 11 meters. What is the magnitude and direction of the electric field set up by the proton at the position of the electron?
What's your distance?
So we've got a proton right here. We've got an electron right over here. And their question is, what is the strength of the electric field right here? that's set up because there is a proton right over here. And they say the distance was how much?
5.3 times 6.
Now, what is the charge of this proton? You might go back to that page, or does it have it on this page? No, it doesn't have it on this page. That page, Brett, do you remember that page number? You'll want to know the charge of an electron, which is the same as a proton, except they're just opposite.
Negative 1.6.
Okay, so for the proton, it would be positive 1.60 times 10, negative 19th, isn't it? Yeah, coulombs. And this one would be a negative 1.60 times 10 to the negative 19.
Where do you get that distance from?
It says it in the problem. It's the average separation between the electron and the proton and the hydrogen atom. So that came from the problem. So what is our equation that tells us electric field strength?
Coulomb's constant.
Coulomb's constant. Charge
Over distance squared.
over our distance squared. Okay, so we're trying to figure out what is the electric field strength right here. So Coulomb's constant is what? 8.99 times 10 to the 9th. And our charge that we have is our negative 1.6 times 10 to the negative 19th.
Over.
And our distance,
I don't think it's.
What's the water?
It's not over all of it.
they're wanting to know the force at this position.
Oh, wow.
Now the negative is really just a direction for us. So when we're done, we're going to be telling about the direction that vector is going.
Is it overall?
Why? I don't think it's supposed to be over the Coulomb constant too, is it?
Yeah, no, it's the same thing.
Oh yeah.
Same thing.
Same
This
thing.
is in the numerator. Coulomb's constant is in the numerator if I had to write it in a fraction. Same thing. So 5.3 times 10 to the negative 11th, and that has to be squared. Try your calculators out. And really, the negative is immaterial to us. We'll talk about the direction of the field independently.
Got 5.12 times 10 to the negative.
So it looks like we only have two significant figures from the 5.3. So 5.1 times 10 to what? 10 to the 11th. What unit is this electric field strength measured in?
Would it be newtons or what is this? N/C newtons?
Newtons per coulomb. Newtons per coulomb, the field strength. And let's tell about the direction of it. So what direction is this electric field strength caused by this? They said it was caused by this.
Away from it?
Has to be going towards. What?
Why is it away from the proton?
What's positive?
Positive?
How do we tell electric field direction? The direction that a positive charge would move. So this negative electron would be attracted to it. That's correct. But the electric field vector is drawn in the direction a positive would go, which would be away from this positive right here.
Away from the proton. Okay,
Away from the proton. Away from the proton. Yeah. So in their reading, if you go back to the problem, it says magnitude and direction of the electric field set up by the proton. Set up by the proton at this position. At this position. So our field was set up by the proton, so the field is going away from that proton.
So we use the positive 1.6. So in this case, one.
The negative and the positive really don't come into play. The direction comes from how we tell direction of an electric field. So your number is going to be the same whether you use a negative or a positive here. We don't determine the direction from the sign of this. We determine the direction from our rules back here that said the direction of an electric field vector is the direction that would be exerted on a positive test charge.
So why do we take out the negative one from the number?
That's the reason. Because the direction is not determined by the sign. I mean, whether you multiply by a negative or positive number will not change the magnitude. It's the same number. And we don't determine the direction by the negative or positive. We determine the direction by this rule. The direction a positive test charge would go, which would be away from this proton, which they are saying is causing the electric field. Electric field lines. We draw lines to represent our electric fields. And the number of lines we draw represents how strong that electric field happens to be. So electric field lines are always drawn tangent to any point that is causing them. So let's look right here. If we're talking about a positive charge, then we just draw a circle with a little plus in it. Negative charge, a circle with a little negative inside of it. Electric field, we just draw an arrow. Capital E stands for that. And electric field lines then are just going to be these lines with little arrows on them showing the direction of that electric field. So we'll see their video in just a minute. But if I had, I'll go ahead and use red since I have red. If I had this positive charge and I wanted to draw the electric field lines, then I would be drawing lines that are going exactly like this, exactly away from that positive charge, because the direction of an electric field is the direction that a positive charge would move. Now notice, all of this has meaning. That wider separation and this narrow separation talks about the strength of the electric field. The number of electric field lines proportional to the electric field strength. Well, this also is true. As I am closer to the positive charge, that is a stronger field there. Then as I get farther away, it's more separated, a weaker field there. And the number that I draw is also significant. If you drew 4 electric field lines down here, 1, 2, 3, 4, 5, 6, 7, act like they're all proportional, 8 field lines up there, we would literally be meaning that this electric field on the top is twice as strong as the electric field on the bottom. So the number of lines will be significant.
So how do you know, like, how many lines?
So how do we know how many lines? If you just are given one charge, then it really doesn't matter. But if you have 2 charges with different strengths to those charges, then we would know that they need to be proportional to those strengths. Like if one is twice as strong as the other, I'd have twice as many on one as the other. Now look at these before I play this. Look at these lines a minute between the positive 2 charge and the negative 2 charge. Well, we know the electric field is going away from the positive and towards the negative. And it always leaves perpendicular to the tangent line at the surface. So all these lines are supposed to be leaving perpendicular to any tangent line. And as this one goes away, it curves because it's attracted to the other one. So this is literally the shape, if you could see the electric field, that it would look like. Have you ever seen a magnet under a piece of paper and then iron filings being dripped on top of it? I don't know if you've ever seen that. They take a pattern that looks like this. We'll do that when we get to magnets, right, David? We'll do that when we get to magnets. Right over here, 2 positives. Notice they are repelling each other, these electric fields, so they don't arrive on the other charge. They are pushed away by the other charge.
Electric field lines are a way of visualizing electric fields. For an isolated positive charge, the lines originate on the charge and continue to infinity. For an isolated negative charge, the lines originate at infinity and terminate on the charge. When 2 or more charges are present, the field lines still obey the same simple rule. The number of lines leaving a positive charge or terminating on a negative charge is proportional to the magnitude of the charge. The third and last rule is that the lines of the same field cannot cross each other.
So you notice none of these lines are crossing each other, intersecting each other. If they would have drawn one with a positive 2 and a negative 1, then there would be twice as many lines leaving the positive 2 as are arriving on that negative 1. So all the extra ones would just be going off. Half of them would be going off the 2, and only half of them would be arriving at the negative 1.
So the one that
That's
left is
the
like
proportional.
perfectly neutral pretty much because they're both, everything is just connected together.
Say that again?
So like so this is a lot like magnets, like repelling and attracting?
It works the same way, it does, because magnetic fields work just like this. We call them flux lines when we talk about magnets. We call them electric field lines when we talk about charges, but yes, they work the same way. So here comes the continuation of that.
For two equal and opposite charges, the number of lines that begin at the positive charge is equal to the number of lines that terminate on the negative charge. Near the charges, the electric field lines are nearly radial. The electric field is strongest in the region between the charges, which is indicated by the high density of field lines.
So there's the density I was talking about. These lines are closer together here. It's a stronger electric field there. We can tell that it's a weaker electric field out here.
For two positive charges, the field lines originate on each charge and continue to infinity. Again, close to either charge, the lines are nearly radial.
Did you have a question?
No.
Okay.
In this case, the electric field has a minimum in the region between the charges, which is indicated by the low density of field lines.
So you actually would have a location right in here that would have 0 electric field strength, even though you are close to those two charges. Why would it be a 0?
Because they're both positive, and
The
so they're
lines
just
can't cross.
Yeah, they're both positive. They're opposing each other. And so you would get a net force or strength of 0 right in that region.
If both charges are negative, the representation of the field will be similar, except that the lines will originate at infinity and terminate on the charges. The field created by a negative particle and a positive particle with double the charge resembles that of the equal and opposite charges, except that only half the lines originating from the positive particle terminate on the negative charge.
So if you counted them up, there would be twice as many lines leaving that positive 2 charge as are landing on this or arriving or terminating on this negative 1 charge.
If the negative particle has twice the charge of the positive particle, the field would be similar. All you have to do is replace the direction of the field lines.
There you go.
Are we going to need to know how to draw these?
So in case you have to draw one of those, there are the rules for drawing them. So if I was going to draw one of these, that was a positive and a negative, so the rules are not hard. So let's call this a +2, so Q equals +2. And this one is just going to be a -1. Q equals a -1 over here. If I wanted to draw my lines, well, I'm going to have 1 that leaves and going like that, 2 that leaves, 3 that leaves, 4 that leaves, 5 that leaves, 6, 7, 8, 9, 10. I've got twice as many that are leaving the red one as are arriving at the blue one. That's as easy as it is. Conductors in electrostatic equilibrium. The electric field is 0 everywhere inside a conductor. So if you have a metal bar that has been charged, and it's isolated, it's hanging here from a thread that's not conducting, so it's just hanging here, this bar that is charged, those charges, the net charges, all reside on the surface. If you could crawl inside that bar, it is neutral. You have the same number as positives and negatives inside it. It's on the surface that those excess charges are going to be residing. Any excess charge on an isolated conductor resides entirely on the conductor's outer surface. This can be expanded to, in that lab when you had what we call the Faraday cage.
Yeah.
Well, if I just made a ball out of metal mesh like that, and I charged up that metal ball, inside that ball would be a 0 net charge. all the charges would be residing on the surface of that net ball, that wire mesh ball that was there. So you would be safe inside that wire mesh ball, even if there were charges that were charging up that Faraday cage, it's called.
So you want to be inside a flow conductor?
So you would be safe inside, like in a car. When you are inside a car, you're inside a metal shell, a type of Faraday cage. And if you have charged atmosphere, a lightning storm around, you're still just fine, because those excess charges are going to be residing on the outside of that metal car frame. The electric field just outside a charged conductor is perpendicular to the conductor's surface. So the shape of that conductor, if it is a circle, it looks just like back over here. If it's a circle, well, those charges, field lines, are just going perpendicular to the surface. They're coming out just like that. So we have, let me draw a slightly irregularly shaped object, something like this. My electric field lines would be going like this, assuming this is positively charged. My electric field lines are going like this, and then they're going to turn over here. It's just going to be perpendicular to the surface right over here. You get the idea. That's all they're saying right. On irregularly shaped conductors, charges tend to accumulate where the radius of curvature of the surface is the smallest. That is, at the sharpest point. At the sharpest point. We're going to get to that picture here in just a little bit. So, if I have a conductor and it is shaped like this, then I am going to have a stronger accumulation of charges here than I will out here. And it has everything to do with the geometry of the direction that those forces are going to be. And when it's sharper, they can get closer to each other. We'll save the demo on this. Yeah, real quickly, you can't there. We'll save the demo on this till everybody comes back, but I'll talk about it for just a little bit right over here. This is my beautiful drawing of a house that has a lightning rod on it. So if we have in a cloud excess buildup of negative charges, what happens is it begins to drive away the negative charges in the things that are close to it, so you'll get a buildup of excess positive charges. So if my charge cloud is above my house becomes positively charged because it drives away the negative charges, just like we did with that balloon and our little electroscope that we had. The ground picks up those positive charges. So what is the purpose of a lightning rod? Well, there's actually a dual purpose to that lightning rod. One is, if the buildup gets strong enough that it discharges, and it's called a lightning bolt, then we would like it to strike that lightning rod, which will have a nice copper cable that runs down into the ground. So a lightning rod is not just a rod isolated sitting up there. It is connected by a wire to the ground. And so it provides a path for the electricity to follow so that it doesn't go through my house and catch my house on fire or blow a hole in my house or something like that. That's one purpose of a lightning rod. The second purpose of a lightning rod is this. That lightning rod is sharp, is pointed.
People have lightning rods in the house?
Most people don't have lightning rods on houses, but most churches that have steeples do have a lightning rod at the tip of that steeple. I need to look recently, but I think our church right out here does. If you look at the tip of that steeple, you'll probably see a little metal needle sticking up above it.
Oh, so they
a lightning rod on it. So purpose number one is if lightning strikes, it hits that conductor and it follows the wire which is connected to that lightning rod around and to the ground so that it doesn't go through the house. That's purpose number one.
The dorm.
Does it? Where's the dorms?
Around.
Right on the tip, on the top? There you go. Okay? The second purpose is because the charges accumulate at a point. Let's imagine this positively charged house. Well, those charges will tend to accumulate excess on this point. And they will, if this is attracting those positives, they will begin to bleed off that lightning rod. Now, if I lose the positive and it bleeds off, it begins to counteract the negative and it reduces the difference in charge. And it takes a big difference in charge for the lightning bolt to strike, to discharge. So if I actually can bleed off enough where the difference is reduced, lightning will not even strike. That is the second purpose of a lightning rod. And when we do a demo, I'm going to do a little demo with a little miniature lightning rod. And you'll see how it amazingly affects, in fact, it will reduce the ability, it will eliminate the ability of my Van de Graaff generators to strike. We're going to have lightning strikes. They're not really lightning, they're static electricity strikes, but that's what lightning is, just much bigger, that are going to be going between those two globes. And when I put my little lightning rod on it, it will quit, even though that lightning rod is actually closer to the globe than the other one was. It will bleed off enough charges that it will reduce the charge difference and it will prevent it from striking. So a lightning rod has two purposes. This picture down here, I'll turn off the lights, came from when I was building my house. And looks like I did have my windows installed, but you see this right here? Here's a close-up right down here. And here's a little closer up where you can see kind of a black line going through here. There's a lightning storm out at my house. And lightning hit evidently the ground or a pole close enough to my house. And there was a generator sitting in here from the construction workers. And they had a wire going out through the window and plugged into the pole. Well, it arced between the feet of that metal frame on the generator and the reinforcement rods, the rebar in my concrete. And it blew this hole of concrete out from the lightning striking somewhere close. The charge went enough and it blew that hole out in the corner there. So that was kind of interesting. A little example of what lightning might do. What?
It's kind of scary.
Yeah, it is. I was out there working laying tile at night, and it was a lightning storm going around, and it began to jump. I could see little sparks jumping from I had power cords that were giving me lights because there's no power in the house, just plugged into the pole outside. And I began to see little sparks jumping from my cord onto the ground, and I could feel the hair standing up, and it was like, I've had enough of this. I pulled the plugs, got in my car, and I went home. So I don't have any desire to be struck by lightning. 17.1. Electrical potential energy. So we just move on with electricity here into 17. So 16, 17, and 18, all about electricity, so that's why they're put together. Electrical potential energy. Potential energy associated with a charge due to its position in an electric field. I want you to think about a gravitational potential energy for a minute. If I raise a mass a farther distance away from, something was going on
Sounds
there.
like classroom FaceTime call.
Yeah, I don't know what that was. Something was coming in.
Something
All right. If I raise a mass in a magnetic field, I change the in a gravitational field, I change the gravitational potential energy. The position of that mass in the gravitational field changes its potential energy. That's the same idea. Electrical potential energy, if I have a charge in an electrical field, depending on the position of that charge, it's going to have a different amount of potential electric energy. So electrical potential energy is just another component of all this mechanical energy that we've been learning about. Total mechanical energy, we can add something else to it now. Kinetic energy, 1/2 mv squared. You know that formula. Potential energy due to gravity, mgh, excellent. Elastic potential energy, 1/2 kx squared. K is the spring constant, x is the distance we are. And now we have electric potential energy, and we'll get that formula here. Electric potential energy can be associated with a charge in a uniform field. So one way of finding our electric potential energy, if we have a uniform electric field, is simply the negative of the charge we have, the strength of that field, and the distance we are from the reference point. however far away we are from our beginning point. Electric potential energy. I'm going to have to turn my sound back on now.
When two charges interact, they exert an electric force upon one another. The potential energy associated with this force is called electrical potential energy. It is a form of mechanical energy that increases as the magnitude of the charges increases and decreases as the distance between the charges increases. In a uniform electric field, the electrical potential energy of a charged object is due to its position with respect to the direction of the electric field. Displacement of the object perpendicular to the electric field does not change its electrical potential energy. Charges that are allowed to move freely will move to positions of lowest potential energy. In the device shown here, electrons exit the central sphere and move to the outer sphere. As this happens, the electrons lose electrical potential energy in exactly the same way that a falling object loses gravitational potential energy. If a person touches the outer sphere, the charge can then pass from the sphere to the ground, where it reaches an even lower potential energy. Charge naturally flows in the direction that results in the lowest electrical potential energy.
So we'll see a demo of that little device. I've got that little device. I've got one of those things.
Okay.
No, when people are back. I'm going to throw these demos together and everybody gets to see them.
Awesome.
So let's look here for a moment. If I have an electric field, so here comes my electric field going in this direction. And I've got a charge. We're going to do a positive charge right here. So there's my positive charge. And if I move my positive charge this way, there is no change in electric potential energy. Just like in gravitational, if I move my arm horizontally, my mass horizontally, I have not changed my gravitational potential energy. If my charge is allowed to move with the field, do I gain or lose potential energy?
Gain, you lose.
I lose. Just like if my mass, if I let it go, which way would it go? With the gravitational field, and I would lose gravitational energy. If I move it against that field, more potential energy is gained. I have to put work into it to gain that. So if I move my charge this way, I'm gaining electrical potential energy. So it works like a gravitational field. Yeah.
Is that relationship parabolic in this case? Because like if you go so far away, won't you start to lose?
Well, I wouldn't say parabolic, but it is related to, let me write that formula that they don't have written right up here. Another potential energy, electrical potential energy formula. Coulomb's constant between two charges. This is the one between two charges over R. So as my R gets farther apart, it's simply proportional to that distance.
Okay.
Now, there was a force, electrical force formula that looked almost exactly like this. Do you remember the difference? The R was squared on the electrical force. So it was still Coulomb's constant, the force between two charges, but that was the distance squared. So this formula looks very similar to that electrical force formula, except this one is just R by itself. This is another formula for getting electric potential energy. This is if I know the field strength and the distance away and one charge. This is if I have two charges, and it should come up over here somewhere. Maybe it doesn't come up over there. So this is if I have two charges and the distance between them. Electric potential, so here's our potential energy that we're talking about, equals the work that must be performed against the electric forces to move a charge from a reference point to the point in question. Per unit charge, that's why they say divided by the charge. So, electric potential, I said energy, I shouldn't have added the word energy. Electric potential, we use V because we measure electric potential in volts. And you're familiar with that word, volts. Voltage is electric potential measurement. So if I take the electric potential energy and divide it by how many coulombs of charge I have, that's where I get my voltage of something. So electric potential associated with a charge is electric potential energy divided by the charge. potential difference. So if I have, let me come back over here. If I have a certain amount of charge, this positive has a certain amount of charge, I could figure out the electric potential measured in volts it has if I know the strength of the electric field and simply divide it by how much charge this one happens to have. Potential difference is if I am in two positions. If I am in this position, I have a certain electric potential. If I am in this position, I have a different electric potential. And the difference between those two positions is my electric potential difference, delta V, which is measured in volts. It's just the difference in voltage between two positions. And that is, if you think of a battery, it has two terminals. If it's those little square 9-volt batteries, what it literally means is between one terminal and the other terminal, there's a difference of 9 volts. It doesn't mean one of them is 0 and the other one is 9. It can be if one of them is grounded, it's 0 and the other one is 9. But I could hook another one up to it. So one goes from 0 to 9, the next one goes from 9 to 18. It's a difference of 9. And in fact, that's how you get bigger batteries. Is you hook, we call it in series, and we'll get to that. But you hook them up together in series, and it's just a step up of potential difference of voltage. One goes 0 to 9. The next one goes 9 to 18. The next one goes 18 to 27. The next one, and pretty soon you have massive batteries with massive voltage on them. All right, so right over here, it's the same thing, same formulas up here, it's just a potential difference. It's a difference between two different positions. So let's see this potential difference video.
If a positive charge is released from rest in a uniform electric field and moves a distance d, there is a change in the electrical potential energy of the charge because of its displacement. The reference point, or 0 point, for electrical potential energy must be chosen. Here the reference point is point A. If the charge returns to point A, its change in electrical potential energy is 0 because the displacement, delta D, is 0. Only the difference in potential energy is physically significant. The equation for the electric potential energy of a charge Q in a uniform electric field E shows the simple dependence of potential energy on Q, E, and delta D. Just as the gravitational potential energy of a mass falling through a gravitational field decreases, the electric potential energy of a positive charge moving in the direction of an electric field also decreases. Since potential difference is defined as potential energy per charge, the expression for potential difference in a uniform electric field is the potential energy divided by the charge. In this equation, displacement is taken to be in the direction of the electric field. Displacement in a direction perpendicular to the field produces no change in potential energy.
So again, if we moved our charge perpendicular here, even though there's a distance, there's no change in energy. But if I move it parallel or with the field against the field, then there's a change in potential energy.
Does the current have anything to do with the amount of voltage?
Yes. Our next chapter, we're going to get into the flow of electricity and the current and things like that. So yes, it does.
So your car battery runs DC.
Your car battery is DC, direct current. Correct. And if on my car battery, I have a positive terminal and a negative terminal. If I take a wire and stick one end on the positive terminal, loop it around and put it back on the positive terminal, is there any potential difference between the ends of the wire?
No.
No. No electricity is going to flow. But if I take it from the positive and loop it around to the negative, there's a difference in potential and electricity is going to flow. But that's next chapter. The potential difference in a uniform field varies with displacement from a reference point. Didn't we already have this one? I think we already had this one.
Yeah.
I probably put it up here because we're going to do a problem now. 585, number 2. Number 2. What is the potential difference between the initial and final locations of the particle in problem 1? Oh, that's a cheating thing. As a particle moves 10 meters along an electric field strength of 75 newtons per coulomb. So let's just get some information down. I have an electric field strength, 75 newtons per coulomb. We're going to move a distance of 10.0 meters, and we're moving with that electric field. Its electric potential energy decreases. So that's going to be, what's that? Well, that's going to be our change in, they say electric potential energy. Oh, they said energy. That's not delta V, that's delta PE. Potential energy loses 4.8 times 10 to the negative 16th joules. 4.8 times 10 to the negative 16th joules. So there's our change in potential energy. So they want to know, problem 2, what is the potential difference between the initial and final locations of that particle? Let me back up over here. I'm not sure that I wanted that one right over here. Oh, I am going to have to. I was thinking I can use this one right here, change in potential energy divided by charge, but I don't know what that charge is. Did they give me a charge?
Yeah, you're supposed to solve from one person.
As a particle, oh, what is the particle's charge? Sure enough. So I'll give you the answer to number 1, I guess. We have a particle's charge of 6.4 times 10 to the negative 19th coulombs. So I don't even want that one right over here. My potential difference, change in potential energy, divided by unit charge. So this one shouldn't be too hard. Negative 4.8 times 10 to the negative 16 divided by this number. 6.4 times 10 to the negative 19.
You know, I feel like on the test it's just not that simple. Ever.
Well, you have to remember the formulas on the test. What do you get? Calculators.
Negative 750.
That's clear. And what do we measure that in? This delta V? Volts. It's measured in volts. Capital V. So we lost 750 volts in that process. All right. The electric potential at point A depends on the charge at point B and the distance between it. Here they've called it R. An electric potential exists at some point in an electric field regardless of whether there's a charge at that point or not. So just remember, whether I have a charge here or not, there is an electric field there. Because of, or charge 2, there's an electric field here. So whether I have another charge there or not doesn't determine whether there's an electric field. It's just how much potential there is going to be, how strong that other charge is. The reference point for the potential difference near a point charge is often at infinity. So we say essentially compared to 0 potential, where are we at? And that's really what batteries are doing. Compared to 0 potential, it's a 9-volt battery compared to 0. 0 up to 9. Potential difference between a point at infinity and a point near a point charge is found by this. So if I want to know what is my potential difference, Coulomb's constant times the strength of the charge in coulombs divided by my distance is going to be how strong it is. Superposition principle. Anytime you see that superposition principle, we're talking about vectors that we can add together all at one point. Can be used to calculate the potential for a group of charges. So we're going to see vectors, we're going to combine vectors. So here's the idea. The electric potential at the center. So how much electric potential energy do we have because of all these other charges that are around this? Is going to be just the vector sum of all these. So that's what they're going to be taught. Oh, it's not the vector sum. It's just going to be the sum of all
According to the
these.
superposition principle, the electric potential at a point is the algebraic sum of all the individual potentials existing at that point. The strength of the charges, their polarity, and their distances from the point in the middle completely determine the electric potential at that point. This is because, in contrast to a vector quantity, electric potential is a scalar quantity and has no direction associated with it.
Let me come up here, because they've already separated and factored this thing. For my potential difference between a point and a charge, the formula was Coulomb's constant times the strength of that charge times the distance my point is away from that charge. So if I want to know what is the electric potential at this point from that top charge, I just would use this first part of it. And then I just repeat it for all these other charges, and they just factored out Coulomb's constant because it appears in front of every one of those. So that's all they've done, is separated and factored it out.
Calculating the electric potential at a particular point is simply a matter of finding a scalar sum.
So this one, we don't need any vectors. We can just add all those values together. Did I not have a problem? I didn't have a problem. So let me make up a problem real quick. I want to know, here is a charge of 2.0 times 10 to the negative 6 coulombs. I'm going to have a point right here. I'm going to have a charge right over here of negative 1.8 times 10 to the negative 6 coulombs. And I am going to have a distance here of 0.25 meters and a distance here of 0.35 meters. I want to know what's the electric potential at this point. So we have a formula. Electric potential is going to be Coulomb's constant times the strength of the charge divided by the distance that I have away from it. So if I call that 1 and I call that 2, Coulomb's constant times charge 1 over its plus charge 2 over its radius. And I'll fill in the numbers and you'll do the math for me. So what's Coulomb's constant?
8.99.
And our charge 1 was a 2 times 10 to the negative 6 coulombs.
Over 0.35.
And our distance was 0.35. The other one was negative 1.8 times 10 to the negative 6. And it was 0.25. See if I can get agreement since I made up the numbers and I don't have an answer to compare it to.
Negative 13,356.
See if anybody else agrees or disagrees with that.
Do we do one where we have to like find a variable? Like, I mean, find one of them, let's say that's not given, and we have to figure it out.
Yeah. Anybody else with this answer? What is it?
Negative 13,356.57.
Yep. Negative. We had two significant figures in this. 1.3 times 10 to the what are you getting? Fifth?
Yeah.
What did we just measure? I mean, what's the unit that goes with this?
Fourth.
Is it the fourth?
Yeah, fourth. Sorry.
Fourth? Volts. Johnny, if we had a variable, what would be different is we would know maybe the answer, and maybe I didn't know what that distance was, and they said, how far away is that charge?
So then you'd have to solve for that?
So then we'd solve for that. I'd divide by my 8.99. I would, well, this is a negative. I would add that fraction, multiply by x, and then divide by that answer, and there it is. It's just the algebra of rearranging it. I'm done talking. Ooh, you've got almost a half hour to work on stuff. 16.3, 17.1.